In last lecture, we have seen about the different characteristics of the antenna in order to study its performance. Today we are going to continue with the characteristics which is called as gain versus temperature. So we know already what is antenna noise temperature, which is given by the formula. This is the formula for antenna the temperature, which is having the two components. One is the brightness temperature and it is due to the background temperature also. So with respect to the antenna noise temperature, today we are going to see about the gain bar temperature ratio, which is the another figure of merit to study the receiver antenna characteristics. So the formula it is given as gain bar temperature. It is measured in decibel and which is given by 10 log G by TA, and the unit is decibel per Kelvin, where G is the gain of the antenna and TA is the antenna noise temperature. So why this quantity is important? Because the signal to noise ratio at the input of the receiver is decided by this ratio, that is gain per temperature. Since here the signal to noise ratio is directly proportional to this ratio. So if you want to increase this ratio gain per temperature, so obviously what you have to do, you have to increase the gain. But increasing the gain will also have this limitation. So if you want to increase the gain, so if you want to increase this ratio, you have to increase the numerator and decrease the denominator. So the numerator is gain. So if you want to increase the gain, you should have the larger antenna, and in the maintenance of the larger antenna will lead to the expensive. So high gain may not be desirable for application which needs the omnidirectional coverages like cell phone, cellular telephone and mobile data network. So there should be a compromise should be made in between the ratio. Next we are going to see about the characteristic impedance. So the what is the characteristic impedance? Is for any transmission line, the characteristic impedance it is represented by Z0, which is the ratio of that voltage by current. So here if it is a lossless line, so this is the general equation, and if it is a lossless line, you will be having the resistive part is equal to 0 and obviously the conductance is also equal to 0. So the resultant the lossless line is equal to root of L by C. And for any transmission line, in order to achieve the maximum power transfer from source to load, you should have the proper impedance matching. That case, the resistance of the load should be equal to the resistance of the source, or the reactance of the source should be equal to the reactance of the load, which means that if the source is inductive, the load should be capacitive to cancel it and vice versa. And here if suppose there is an impedance mismatch between the source and the load, or the source point to the destination point, means you will be having different types of losses due to the reflection. So whatever the amount of impedance mismatch we have, so the that much amount of reflection will get back to the source from the load instead of transmitting from source to the load. So there are different types of losses like attenuation, reflection, transmission loss, and return loss, and insertion loss. So what is attenuation loss? It is due to the absorption of the signal in the transmission line, and which is given by this formula, which is measured in decibel. So 10 log 10 of EI minus ER divided by EP, where EI is the incident field strength and ER is the reflected field strength and EP is the total electric field strength. And the second one is reflection loss. This loss occurs due to the reflection of the signal due to the impedance mismatch, which is given by 10 log 10 of EI by EI minus ER. So it is contributed by the reflected power with respect to the incident power. And the transmission loss, this is a loss occurs while transmitting through the transmission line. So it is given to the ratio of incident electric field divided by the total electric field. And the next one is return loss. It is due to the reflection, purely depend upon the reflection due to the impedance mismatch. So it is a power reflected by the transmission loss, that is given by 10 log 10 of EI by ER. So the two components of incident and the reflected only. And insertion loss, the loss that occurs due to the energy transfer using the transmission line compared to the energy transfer without the transmission. So something we have inserted in the transmission line means in addition of the insertion, what will be the increase in the loss? That is called as the insertion loss, which is given by E1 by E2. So where E1 is the amount of energy received without the additional insertion equipment, and E2 is the energy received in the receiver after inserting the particular device. That is the meaning. And this is the one of the provision we have to reduce the impedance mismatch between the any 2 point. So the load impedance mismatch, the source impedance, which is called as the impedance mismatch, which can be reduced. The effect of impedance mismatch can be reduced by the method which is called as stub matching. So that is a process of connecting the section of open or short circuit line called stub in a shunt manner with the main line at the point where we have to reduce the impedances, right? So there are different types of impedance matching, that is single stub and double stub. Single stub means, so here this is a stub, here this is the meaning of short circuit stub. So here this is a source point and this is a load point. So if you want to reduce the impedance mismatch between the source and the load point, you have to connect the short circuit stub in a shunt manner between the 2 points where we have to reduce the impedance mass. Excuse me. If you want to, if you connect the two numbers of stub in a shunt between the source and the load point, that is called as double stub. So the single stub is not suitable for coaxial line. That's why we go for the double stub, where we have the two stubs of variable length are fixed at a certain position like this, right? So here this is a single stub and this is this double stub. This double stub matching, it is widely used in laboratory practices as a single frequency matching devices. Thank you.